Hey guys, this is our week 2 review video for Honors Chem. So I am going to go over a couple things this week on Keq, what it means, and we already kind of did how to calculate it, although I will do a little bit more with it, how Keq relates to Ka and Kb, and then running an ICE table. So being able to predict initial concentrations or predict concentrations at equilibrium and relate that back to Keq and see if it makes sense. Okay, it might make sense. I don't know. I just kind of chose some random numbers, so we'll find out in this case. Okay. All right. So first thing I want to go over is I thought of this today of a way to kind of explain Keq a little bit better. So what we notice on the left over this one, Keq greater or Keq less than 1 means it's reactant favored. Sorry if I seem like I'm crazy, but on my camera this is backwards, and so I'm trying to like read the screen backwards, but I know that it's filming correctly, whatever. So Keq that is less than 1 is something that is considered reactant favored. So what that means is that essentially once it reaches equilibrium, the reactants would be a higher concentration. And so looking at this graph, if the y-axis of the graph was concentration, the x-axis is reaction progress or kind of time, what we would see there is that the reactants would be higher. So a Keq less than 1 means it's reactant favored. That literally means the concentration of the reactant should be higher at equilibrium. Now, if a Keq is equal to 1, there's no favor. That particular one, by the way, very rare. In case you haven't noticed, we really haven't had any that are like that. It's not extremely common to see Keq of exactly 1, because in most cases it's going to be favored on one side or the other just based on electronegativity and inertia and all kinds of other things. So very rare, but if Keq was equal to just 1, that means that there really is no favor, and so the reactants and products at equilibrium are the same. So once they level off and their rates are the same, the concentrations are also the same for something with a Keq equals to 1, but that is very rare. So very rarely will the concentrations of the reactants and the products be the same at equilibrium. That's not what equilibrium means. It means that the lines level off because the rates are the same. So then over on the right side, a Keq that is greater than 1 means that the reaction is product favored. And so if it's product favored, I guess I could come over to this side. I don't know why I was getting further. If it's product favored, then of course that means at equilibrium that the products would be a higher concentration than the reactants. So on this graph, you can see that the products ended up being a little bit higher. Okay, so that's what Keq means, and kind of like why it matters in terms of equilibrium is kind of figuring out, okay, well, if I run a reaction to equilibrium and I make sure that it essentially gets to equilibrium, what am I going to have more of? What's going to be there? What's actually going to be in the container? And so if it's something that's product favored, then I can predict that in that container is going to be mostly product, and so I'll be able to handle it accordingly. If it's an acid or something and I need to neutralize it, I would know that I need to neutralize it. If I'm trying to collect it, then I could say, okay, well, it's a product favored reaction, so that's going to affect my limiting and excess reactant, right? It's going to affect how much I can actually produce of the product. So there's a lot of kind of reasons why Keq comes up. Again, we're not going to use it a whole lot more after this unit, truth be told, but more advanced chemistry courses obviously would use it in that way, using it in stoichiometry, etc. Okay. The other thing I wanted to go over is an ICE table. So it looked like from the worksheets that I graded up through yesterday, it looked like most of your ICE tables were looking really good. Those of you that did the ICE tables on the practice or did the ICE table extra practice and attached that with the Keq practice, I am not expecting that you have to, because that's my fault that it didn't have it on there. But if you want some feedback on it, then I would recommend that, because what I've been doing for the most part is if everything looks pretty perfect, I'm just putting 10 out of 10 saying looks good. If it's not, I'm writing a comment back saying, hey, check this one. It seems like you may have put the products in the wrong place, or it looks like you may have interpreted your Keq wrong, or check back on your ICE table, whatever the case is. Okay. So I made this ICE table up. I hope it works correctly. We'll find out. But I just plopped some data there. So this is the ICE table for the dissociation of carbonic acid, which, by the way, is a weak acid. Think about that. So carbonic acid dissociates and produces hydrogen ions because it's an acid, and then its conjugate base, which is HCO3 minus, or the bicarbonate ion. So I've identified that the initial concentration of H2CO3, or the carbonic acid, is 1.0 molar. And then I have identified that the equilibrium concentration of the hydrogen ions and the product is 0.42, okay? So what we're going to do there is, first thing we need to do is kind of figure out, well, what is X, okay? So the first thing I do when I look at this equation is I check to see, is the mole ratio correct? Is it balanced correctly? It is balanced correctly, because when acids dissociate, they traditionally just kind of kick out individual parts and just decompose, essentially. And most decomposition reactions are like that. So then I noticed that both of my products do not have an initial concentration, but since they're products, you start with none, right? If we're assuming that we are just taking carbonic acid and immediately dissociating it, we have no bicarbonate and we have no hydrogen ions. So we would start those initial concentrations at 0.0. So 0.0 molar, 0.0 molar, okay? So if you want to work this one out with me, you can pause the video right now. I'll give you a good... there it is. So if you want to pause the video, write it down, you can work it out with me. Or if you just want to watch me go through it, that's fine too. But both of our products, hydrogen ions and bicarbonate ions, start at 0, okay? Now, the only piece of data we have is the equilibrium concentration for hydrogen. So all three of these are 1:1:1 ratio, which means they're all going to be just X, okay? So we're not going to have to do any sort of multiplying or dividing or anything like that. They're all just going to be X. So this is a pretty simple one, and this is mostly what you would be assessed on, are going to be pretty simple ones, and mostly dissociation of acids, although, you know, it might be slightly different, whatever, we'll see in a second. So what we see here is the hydrogen ions went from 0.0 to 0.42, which means they went up by plus 0.42, okay? So the C, or the change for the hydrogen ion column, was 0.42. We went up by 0.42. So what that means is that the other product went up by the exact same, because if it's a 1:1 ratio, then whatever was created of hydrogen ions is created of the other. So that means it also went up by 0.04, or excuse, by 0.42. And then that means that our final for that one is going to be 0.42 molar as well. So both of those products did that. Now, while both of those products were formed at the same rate, the carbonic acid was broken down in the same rate, which means it is a minus 0.42. Okay, minus 0.42, because it's a reactant, which means it went down. Reactants are used up to make the product. And our assumption here, of course, is that we're talking about the forward reaction. If it had specifically said the reverse reaction, well, then these values would have changed. But our assumption is we're working with the forward reaction. So 1.0 minus 0.42, can I do this? 100 minus 42 is what, 58? Yeah, I did it. All right, so 0.58. I didn't want to do the decimal, so I just said, all right, well, if I had the same number of decimals and I moved the decimal the same, I'm just going to subtract it and then move the decimal back. Ain't no unit on that. Oops. All right, so 0.58 and 0.42 and 0.42. Okay, so let's, it says here, calculate Ka for H2CO3. K is a constant calculation, so it's always going to be done with the same expression, which means for this one, it's going to be bracket H plus, bracket HCO3 minus, over bracket H2CO3. Okay, so this is my equilibrium expression, and I'm going to zoom out so you can see, zoom out, right? So you can see the equation at the top, so it makes sense. And then I'm going to go ahead and just plug everything in. So that's going to be 0.42 times 0.42 divided by 0.58. I really hope this works out the way I was hoping it would work out. Of course, I didn't get my calculator out. So the next time I give y'all crap for not being prepared for something, y'all can say, well, remember that one time? That second time you didn't have your calculator ready? All right, so 0.42 times 0.42 divided by 0.58, and I get a value, I get a value of 0.30, okay? So my value came out to be 0.30 because that's my sig figs. Looks like 2 sig figs, essentially. So 0.30 is my KEQ. So that means it's a KEQ, or excuse me, KA, KEQ, KA, it's the same thing. It's just when you say it's KA, you're saying it's about an acid. If you say it's KB, it's about a base. If you're saying KEQ, you're just saying, well, it doesn't really matter. It just is some, right? So the KA here is significantly less than 1. That means that this is reactant favored. So we have a Ka of less than 1 or a KQ of less than 1. It's reactant favored. And let's go back to what we said. Carbonic acid is a weak acid. And what that means is that carbonic acid is not going to fully dissociate, which means that when it does dissociate in water, it's going to be predominantly carbonic acid still. Only 10 to 15% of it is going to be this, which makes sense because it's reactant favored. So a weak acid will always have a Ka of less than 1 because they're never going to fully produce. They're never going to fully produce. Hi, Mia. They're never going to fully produce enough to get a Ka of greater than 1. Okay, so hopefully this has been informative. I just want to make sure you guys see that she is putting in some work on this ice table. She can do it, so you can do it, right? All right, Mia, say hi. Hi. All right, cool. That's enough. All right, so that is our review video. You guys have a quiz that I want you to make sure you finish before the end of the day tomorrow. She just laid down on the KQ graphs. Oh, she's out of here. All right. So anyways, make sure you take that quiz for the end of the day tomorrow, and I will talk to you guys soon. Another quick heads up, because it's not technically posted on Google Classroom yet, next week, week 3 of our distance learning is the end of this unit on equilibrium. So we will be assessing at the end of next week. So make sure that you are putting in the time this week and moving into next week to really review back through the initial part, which was really just equilibrium as rates are equal. All right.